Now let us study the presence of multiple theories in a single formula and how to solve them together, which is called theory combination. So what happens is usually problems don't show up as in an isolated theory. They involve multiple class of functions and predicates. For example, you may have array, you have linear arithmetic, and may have unknown functions, and they all show up together. And therefore, you need to apply reasoning of all these domains to solve the formula. This is called theory combination. So there is a standard method which helps us solving this formula together, which is called Nelson-Optimum method. So let's first fix our notation. Let's suppose you have a Q theory involved in a formula T1 to Tk. We will assume that we have decision procedure for each quantifier free theory Ti, and we will have in this lecture assume all the formulas are quantifier free. So we will present a method that combines the decision procedure of each of these individual theory and provides a decision procedure for the quantifier free formulas in this theory. So that's called, as I said, Nelson-Optimum method. So let's study what is it. So when this method is applicable, if the following condition holds: each of the theory has its own distinct signature and they don't overlap with each other. Each theory is stably infinite. I will explain what that means. The formulas are conjunction of quantifier free literals, and this restriction is not important because at the end we will have this structure. The disjunctive structure is handled by our CDCL algorithm, and when we comes to theory solving, we always handle conjunctive formulas. So this is not a real restriction. The important bit is this stably infinite. So let's see what is stably infinite. The theory is stably infinite if for each quantifier free satisfiable formula under the theory, the formula is satisfiable in an infinite model. It should not happen that it is satisfiable but there is no model that is infinite. Yeah? But what does that mean? And it's a very strange condition at the first viewing, but eventually it will be clear what it means. So here's an example. When if you have this axiom in your theory, and which says that if you have three variables x, y, z, either x is equal to y or y equals to z or z equal to x. This is basically saying is that in your theory there cannot be more than two elements. This theory is not stably infinite. It can be a formula, like true formula has a model which has two elements in the universe, but there's no infinite model. So we call a function of a predicate in SI as I symbol, just for convenience. A term T is an I term if the top symbol is an I symbol. Not all the symbols, just the top symbol should be an I symbol. An I atom is an I predicate atom, or S equals to T, where S is an I term. S is an item, T is not required to be item. V is a variable and T is an item. Sometimes let's suppose V is equal to f of x. So then you will say, well, this is an equality term because f of x is appearing, f is an uninterpreted function. An I literal is an I atom or the negation of one. Usual definition. Let's look at it. Let's try to understand why the definition means x plus y is in the theory of integers because it has a top symbol is plus, which are coming from this theory. And then look at this, the top symbol is stored, therefore it is coming from theory of arrays. So let's continue our definitions. An occurrence of a term t in I term or literal is I alien, okay, if T is a J term, T itself is a J term, which is not same as I, and all its super terms are I terms. Okay? An expression is pure if it contains only variables and I symbols for some I. There's nothing else is happening. The only I symbols are there, and no other J symbols are going around. So consider this. Look at this. This is my equality, and left hand side has a top function read. So therefore it belongs to theory of arrays. Therefore this is a alien term, and it is coming from theory of equality. Similarly, z equals to 3 plus y. There's nothing is alien in this term because right hand side has a plus and left hand side is just single variable. So this belongs to theory of integers and nothing is alien. In this equality, you can see that this belongs to theory of equality, but the symbol 2 appears from the integer world. So therefore this 2 is an alien. Now let us look at how to convert to separate form. What we will do, we will take a formula f as a conjunction of literals, and we contain a conjunction of formulas f1 to fk such that fi is a ti formula. It does not contain any symbol from any other theory. It's in pure form, and all the alien occurrences have been somehow removed. Let's see how we do it. Let's suppose we pick an I literal L from formula f, and then remove this literal from the f, and then we want to add this into our in our FIs, right? So if L is pure, then you just go ahead FI, take a union with L, okay? But otherwise we need to clean it up. So what do? We pick the term T, okay, occurring I alien, which is alien in the literal L. And what we do, we pick a fresh variable z and replace t by z. Okay, just remove the t and put the z in your literal. Add another equality, z equals to t. Now this thing is not an I literal, okay? It is, belongs to another theory because it's a variable and equals to another term, which takes it away from the ith theory. So that's how you keep doing it, and eventually you will have a pure formulas. Okay. For example, consider this formula. Here you have x is between 1 and 2, fx is not equal to f2, and fx is not equal to f1. So it involves two theories, equality and integer. And what do? We have 2 and 1 are the alien terms. Since here, look at 2 and 1 is occurring here, and this whole thing is about equality, and 2 and 1 is about integers. So they should go away, and we should add in replace n by in variables z and y, and we have to say that y is equals to 1 and z is equals to 2. And since they are belong to theory of integers, so they move there, and otherwise others are moved theory of equality here. So let DPI be the decision procedure of theory TI, and F is unsatisfiable. If any one of FIs become unsatisfiable, then you are done. Okay? If all DPI FI return satisfiable, we cannot guarantee satisfiability. How do we know that the values assigned, they have a common variable names? So if a value is assigned in one particular theory may not match with the values assigned for another theory, so there must be some coordination among them to find satisfiable assignment. So this coordination is called theory combination, and it is done via Nelson-Oppen method. The trick is this: what we do, we need to know all the common symbols, which are, let's say, S, and which of them are equal to each other and which of them not equal to each other. So let's suppose I have equivalence relation over S, and then we say that the formula corresponding to equivalence relation is if two terms occurring inside the S are equivalent, then we will say T equals to S in the formula. If they are not equivalent stated by S, then we will say T is not equal to S. You note that as soon as we have two equivalence classes of terms which are not in the same equivalence class, it doesn't mean that we don't know anything about them. We actually this say that they are not equal. This is important fact. You cannot just say that we don't know what their relation is. Either they are equal or they are not equal. We'll use these formulas for equivalence relations for our coordination. Now let's see how our Nelson-Open method works. Let T1 and T2 be two theories with disjoint signature. We will take a conjunction of literals for theory Cn, T1 union T2. The convert F to separate form, okay, F1 and F2, okay, they belong to these respective theories. The guess an equivalence relation tilde over these variables which are occurring in both F1 and F2, and run the decision procedure in F1 conjuncted with this equivalence relation formula and F2 conjuncted with this equivalence relation formula. If there is this equivalence relation such that steps 3 and 4 return satisfiable, then the formula is unsatisfiable. Otherwise, formula is unsatisfiable. Remember that there is a guess step is required. This is a non-deterministic algorithm. You make choice of equivalence relation among the common symbols, and then you run your decision procedure for both the theories. And if they come back satisfiable, then you have satisfiability. If you're not, then you don't know that. You need to run for all possibilities. So here's an example. We remember that we had a formula, we had separated into two parts. Now let us consider them again. The common symbols are x, y, and z, and these are the possible equivalence relation among them. All three are equivalent. X, y are equal, but y, z, and z, x are not equal. Okay? Similarly, you write down all possible equivalence relation among them. And you can easily see that this is inconsistent with the f of e. This is saying all three are equal. If you say all three are equal, that is not possible. Okay, so then f of x equals to f of z, and this contradicts. Okay. If x and y are equal, then this is also will contradict. Okay, so all these three choices, when you try to make x or z equal or x and y equal, then contradict with the theory of equality. Let's look at last two possible choices. In this case, I am saying x is not equal to y and z is not equal to x, and y is equal to z. Here, since you said y is equals to z, and here y is not equal to z in this case, so therefore this is inconsistent with this theory. Now I'm saying all three of them disequal. So x, y, and z, all three are disequal. So x cannot be equals to 1, and x cannot be equal to 2, and x can only be in between the range of 1 and 2. So therefore this is unsatisfiable. So therefore, no matter how you guess the equivalence between these three variables, it becomes unsaid. Therefore the whole formula is unsaid.